Hello everyone, welcome to Dakshina e-classroom program. So in last lecture we started new chapter, that is electromagnetic induction. We saw how a changing magnetic flux, when it is linked to a coil, it produces EMF, and that was given by Faraday's, we studied as Faraday's law, and we saw a few simple example of Faraday's law or application of Faraday's law. Let's continue with the same chapter, and next topic is Lenz's law. So Lenz's law is also like sort of related to Faraday's law. It's like nothing much new here actually. It gives you the direction. So here I will write, it gives the direction of induced EMF or induced current in the coil or circuit. So what it says, according to this law, the direction of induced EMF or induced current in the circuit is such as to oppose the cause that produces it. That this is simply termed as Lenz's law. So Lenz's law is nothing, it gives you the direction of induced current or induced EMF in the circuit, and that direction will be how it will be in a way or such as to oppose the cause that produces itself. I mean, like whatever the cause, what is that? I mean, like changing flux. Changing flux is producing magnetic EMF or current. So direction of EMF or current will be in a way or such as to oppose that changing flux, and this is defined as Lenz's law. It is also based on conservation of energy principle, and here we can see even like how it is exactly based on conservation of energy principle also. And another thing is, like, let's say here we have one coil and it is, let's say, like fixed, and now what we are bringing another bar magnets, north and south pole. So let me write, this is the back side and the coil is like this. Now you can see as this bar magnet is brought closer, right? As this bar magnet is brought closer, so you can see in this situation what is happening. Flux is linked to this coil, right? And this is the north pole. This is the north pole and this is your like coil. So now I'm holding this coil. So now when this bar magnet is moving closer, flux through this coil is linked and it's increasing, right? So the direction of current in this coil will be such as to oppose. And what is the cause of induced EMF or current in this coil? The cause is the increasing flux due to this bar magnet, right? So in this coil, the direction of current will be such as to oppose this cause, and like oppose this increasing flux. To oppose this increasing flux, what will happen? So here it will like see north pole and it should oppose it. So opposing it means here the induced current should induce EMF or like magnetic field such as this is north pole and this is south pole, and you can see for that the current in this coil should be in this direction. As seen from this side, it will be in anti-clockwise direction. So this is my outer and this is inner, so the current will be in this direction. So you can see this induced current will have north pole this side and south pole this side. So you can see north pole, and it will repel. It should be opposing this. It's approaching, and this induced current will oppose this approaching magnet, right? So here the direct induced current will oppose the approaching magnet. that way, like this is the way like we can write or we can find the direction of induced current. And similarly here actually, because Lenz law, sometime in problem it's asked like not more about this, like Lenz law is based on what. So it's actually based on conservation of energy principle. Let me tell you how it. So it's conservation of energy principle, right, and how it is. So let's see, in this case again I am considering here one coil, and this is the back side and this is the front side of the coil. So this is a coil, and again this is a bar magnet, north pole and south pole. So let's say I am holding this coil, so it's not in position to move, and this coil is given some velocity v, right, and let's left it. Now what will happen as this coil is approaches? First thing is, we have already understood the current in this coil will be in a way such that it's producing this current carrying coil will also produce magnetic field. So the magnetic field produced by this coil will have north pole in this direction, north pole this, and north pole they will oppose, they will repel. So this bar magnet will feel the opposing force due to, or repelling force due to this north pole, which is the field due to the induced current, right? And now how, see, so now in this case what is happening, if it is given simple some velocity, what will happen actually here? So it will have some kinetic energy, right? And now if this is being held, in this case what will happen, it will induce current in this direction such that here like here this will have north pole and south pole. This north pole is due to the current or induced current in the coil, right? Okay, so this will feel this like bar magnet will feel the opposing force, right, in opposite direction. So it will definitely slow down. Now it's slow down means it's losing some energy, and where that energy is going, that energy will be like, as current is flowing in this coil and some resistance will be there for the current for this coil, so that current will produce some heat in the coil. So this lost in the kinetic energy of this bar magnet will be converted into the heat in this coil, and that way this energy is conserved. So energy is getting lost from here and it's basically utilized here in the, or you can say used in the production of heat in this coil. So this way we can say the Lenz law is based on the conservation of energy principle. So bar magnet will feel the opposing force, and that will slow down its speed, right, and this reduce in kinetic energy of bar magnet will converted into heat in the coil due to current and resistance in the coil. So this proves that Lenz law is actually also based on conservation of energy principle, and this is all about Lenz law. So Lenz law is, it simply give you the direction of induced current or EMF, and that will be such as to oppose the cause that produces this current and EMF, and it's based on conservation of energy. That is how you can understand it. So this is about Lenz law. Okay, so next is motional EMF, what it is exactly. So here let's consider this space, and where we have magnetic field in inward direction, right, like this way. Here this cross, I hope you already understand, that means the magnetic direction of magnetic field is inward and its magnitude is given by D. Okay, and here I am considering one conducting rod. So let's say this is a conducting rod, its length is taken as L and it's moving this direction with velocity V. So now what happened actually when a conducting rod move in a magnetic field, then you can see here this conducting rod is cutting the magnetic field lines. So that means by Faraday's law I can say there will be EMF induced in this rod, and this EMF you can write is coming due to the motion of a conductor or motion of a rod in the magnetic field. So the EMF induced in this rod is also called motional EMF. So here I can write when a conductor or a conducting rod move through or a magnetic field as it cut the magnetic field lines. So EMF is generated or infused in the rod. This is called motional field, right? In this situation, if rod is moving in magnetic field B and velocity v and length L, then this EMF equal to E is given by dVL, and I will also write it in different way. So let me explain this. So simple, this motional EMF when a conductor moves through a magnetic field and cutting the magnetic field lines, there will be EMF induced in the conductor or in the rod, and that is termed as motional EMF. In this situation, remember that it's not general, I'm not writing its universal result. I will tell you different cases also. So in this situation, if this is a rod moving perpendicular to the magnetic field and in this direction, then this is the magnitude of EMF induced in the rod. So explanation based on Faraday's law. Explanation of motional EMF based on Faraday's law. How we can understand this motional EMF or EMF induced due to the motion of the rod in the magnetic field based on Faraday's law. So now you can see here, if it is moving with the velocity v, is it? So then in time dt, let's say the rod has moved here, the flux area covered by this, is it? So let the rod move for time delta t, and distance covered in magnetic field by rod, is it, in delta t, that I can add this is equal to V into delta t, this, and B is what? Number of magnetic field lines per unit length. I will write B is the, actually I write magnetic field lines. We know B is what? Magnetic field, so I can write magnetic field lines will be proportional to B. So in this case, this is this length and this is L, so area covered by rod in delta t time, that will be L into V into delta t. If B is the magnetic field lines per unit area, then I can write magnetic flux or magnetic field lines cut. Magnetic field lines cut by rod in delta t time. This I can write B L V delta t, right? And this you can write, this is the flux. Magnetic field lines cut is the flux. So this implies if I divide delta phi divided by delta t, then that will be the EMF. So magnitude, this is EMF magnitude, and that is equal to BLV. Is it? This is the explanation based on Faraday's law. Faraday's law is when a rod move across number of magnetic field lines, it is cutting. Is it? So that also produces magnetic field, or so that also produces EMF. So B means it's proportional to magnetic field lines. So I do B is magnetic field lines per unit area, and then if it is moving with velocity V in delta T, then this is the distance, and length of the rod is L, so it's covering this much area. So area covered is this, and the magnetic field lines cut by this, or that is equal to flux equal to this, and flux divided by delta T will give EMF induced in the rod. So that way we can understand. Another thing is we can also see, so like initially, let's say if this rod is here at T is equal to 0, and this is at delta T time, so this is the area covered, right? So area covered by rod in delta T, that I can write L V delta T. So this, and the change in flux, that you can write delta phi is equal to what? V into area, that is L V delta T, and this implies delta phi divided by delta T is equal to V L V. This is the EMF. So this way also we can understand the EMF induced. Okay. There is another explanation. Okay, let me just erase that first. We can understand this motional EMF also based on this induced EMF on the basis of magnetic force. So you know, actually in magnetism, again I am assuming you are remembering that when a charged particle is moving through a magnetic field, it experiences a magnetic force, and that is given by F magnet is Q V bar cross B bar, right? So again, let's consider this is the space here. Magnetic field is existing in this space, and the conductor is moving through this space with velocity v. So let me write, this is my conductor which is moving with velocity v. So now what is happening? All the charge carriers, means electrons in this conductor, will be also moving with the conductor with velocity v, right? So now here you can see, let's say this is one electron. So this electron will also have velocity v, and magnetic field B is inward. The force on this electron will be what? E V bar cross V bar, right? So V bar cross V bar, so force, if it is on a positive charge, will be upward, but it's negatively charged, so force will be like this, force will be downward. So what will happen? As this rod moves forward, the electron will experience downward force. So because of that, these electrons will start accumulating downward. Is it? So here electron will start accumulating, and there will be some positive charge on upper surface. Is it? Or upper end of the rod as it's moving here. Right? Now what will happen? This accumulation will continue until some electric field is produced. So let's say E is the electric field. Accumulation of electron on lower end will continue. Is it? That results in some electric field in this direction, and this electric field, what will happen after some time? Next, now see here, there we have another electron, and now on this electron, if electric field due to this negative charge, positive charge in this direction, so what will happen? This electron, the force due to electric field will be F due to electric field, and this is the force due to motion. So if these two forces are equal, then no further electron will move downward, and a constant potential difference will be generated across the ends of the conductor, and that potential is our EMF. Let me explain it more. So just imagine it here. I am drawing a little bigger diagram. So let's consider this is the rod, right? Same rod. I am just to make you understand. So what is happening here? Negative charge, negative charge, negative charge, negative charge, and here positive charge, positive charge, positive charge, positive charge. Now next, so some electric field is generated in this region, and electric field will be downward direction. Right? Now next, this is, let's say, electron. So due to on this electron force, this first thing is downward direction. This is E, magnitude of electric field. So force on this electron due to one will be due to this is magnetic force, that is E V bar cross B bar, and due to this electric field it's downward and force on the electron will be upward. So this is the force due to electric field. Right? If these two forces balance, here I have written this like this is also force due to magnetic, and this is the force due to electric field. So if these two forces, right, when these two forces balance, then no further accumulation of electron will take place here, and that will result when some constant electric field or some EMF is generated across the ends of this conductor rod. So this implies I can write this E into electric field is equal to what? E V bar cross B bar, right? This E gets cancelled. This implies electric field is equal to what? This is equal to V bar cross B bar. And we know actually if E is the electric field, uniform electric field, then potential difference or EMF is equal to what? E into L, or E into L, E times L, and this implies L into V bar cross B bar, and this is exactly EMF. And here we are getting this will be positive, this will be negatively charged, right? So this way you can understand that when a conductor moves through a magnetic field, EMF is induced across its ends, and that EMF is given by VBL. This is also VBL because here velocity and magnetic field both are perpendicular, so the angle between these two is 90 degrees. This will be simply V into B into L. So EMF induced is VBL. So here a conductor moving through magnetic field is equivalent. So let's say this is the conductor. So this conductor is equivalent to what? It's like equivalent to some EMF here, some rod, and it will be like this. So this is EMF that is equal to VBL and or BBL, and its resistance. So this conductor will be treated or can be equivalent to this. It's like sort of a cell EMF, and that is equal to this. So and this is simply termed as motional EMF. So by this time you must be clear what is the motional EMF and why it produces. How we can understand? We can understand it based on either like two way, that is magnetic force on a current carrying magnetic force on a charge or electron, or either from Faraday's law that conductor moving, then it's crossing or cutting some magnetic field lines, and magnetic flux is also changing. That way also it is resulting in induced EMF, and we call it motional EMF. So it's given by simply motional EMF is equal to BVL. B is the magnitude of magnetic field, V is the velocity, L is the length. So this is a simple case. Next thing is, let's say I'm just doing a little bit some changes. So if let's say here also this is the magnetic field existing in this space in the perpendicular direction, right? And one rod, it's like very thin rod, it's moving now not in this direction, it's moving this way, right? Length is L, this length is L, right? Magnetic field is B. So what is the here EMF induced in the rod? So definitely here actually you can see this it's moving, its thickness is moving this way. Magnetic field lines are there, so it's not cutting much magnetic field lines. If I am taking this thickness very small, then I can say almost it's not cutting any magnetic field lines. Is it? When it is moving this way, then it will be cutting magnetic field lines. Is it clear? So in this situation, if width of rod, the rod is taken negligible, then no magnetic field line is cut by rod. So here we can write EMF induced will be 0. Right? In this situation, there will be no EMF induced in the rod. Clear? And similarly, if let's say rod is moving at some angle, is it? So another case here I am considering. Again, this is the space where some magnetic field is present, and now this is the rod, and it's moving at some angle, let's say theta. Clear? So its length is L, its velocity is this way, and magnetic field is V. In this situation, what will be the EMF induced? So this you can write actually that this situation is equivalent to this rod moving in this direction with what? V cos theta, plus this rod moving in this direction with V sin theta. Right? So now this is my effective velocity, let's say V prime. Now you see, if I just look at it this point, in this situation, this rod length L, magnetic field B. So what is the EMF induced due to this motion? You can write it's 0. Due to this motion of rod, this is equivalent to here. Rod is moving this direction, so it's equivalent to moving this direction and this direction. So this plus that, and you can easily imagine here no magnetic field lines are cut by this rod, so that's why EMF due to this motion of rod is 0. Only its velocity is V prime. So here EMF, I can write it's V and V prime into L, right? So this implies that is equal to V L sin theta. Is it clear? Right. So this way you can write EMF induced is V L sin theta. So we need to take the angle actually between velocity bar and L bar also. So I hope you understanding things here. So in this case, the EMF induced across the ends of rod is given by BVL sin theta. Remember that. So next thing is, let me just first erase this. Okay, so consider next case when a loop is moving through magnetic field. So let's assume this is the space having magnetic field B, and I'm having one loop. Okay, so let me consider a loop like this. This is a complete loop. Now as it's moving through the magnetic field, the magnetic flux through this loop, you can say it's always remaining constant. Is it? As loop move through B, phi remains constant. So that means in the loop there is no EMF induced. So EMF induced in the loop will be 0. Right? We can write here. But like just look at it. If I break down this, let's say it's A, B, and this is C. So in this case, now first thing is like overall EMF induced in the loop, if I consider, because there's no change in flux. Flux is there, but as it's like here and as it will be here, there is no change in flux. So EMF induced will be 0 in the loop. Is it? But if we consider only part AB. That means it's just a rod. Let's say it's moving with velocity v. Earlier also it was moving with velocity v and this length was same. Still the EMF induced in the loop, complete loop, is 0. Now if I am taking only part AB, then I can write EMF, this rod. So in this situation, EMF across AB will be BVL. Definitely across AB will be BVL. So this implies, right, this implies there must be some EMF induced in this curved part also, right, across this implies in the curved part or next part ACB also some induced EMF will be there, right? So in this situation, again, let's say this is the region having magnetic field and I am taking, so now again I am carrying forward it. So here you can write this EMF is induced is, that is E BVL, and let me write here EMF induced in this is some E. Clear? So then I can write here as in the loop, so EMF induced in AB is BVL and this is C. EMF induced in AB is BVL and in ACB part let it is E, right? And then what I can write, this implies I can write go in the loop KVL in the loop. This implies BVL, right, plus minus E will be equal to 0 because across the loop EMF will be 0 and from here I am getting E is equal to BVL. It's something important, good result here. The point here is that doesn't matter whether we are having a straight wire or a curved wire, the EMF induced in both the wires is same, is it? So EMF induced in both wire or conductor is same. So this implies I am getting something important result. So again let's consider here magnetic field B, and if I am having any random shape conductor and this length is L and it's moving this direction with velocity B and magnetic field is B. So this is a random shape conductor, is it? So EMF induced in this random shape conductor is also EMF is equal to BV into L, where what is the L? L is the length joining both ends, is it? Length joining both ends of conductor, that is termed as L, right? So in this case, if it is moving at some angle theta, then again we need to consider BVL sin theta, BVL cos theta, so on. But if it is moving like this ends, is it? So ends joining, this is the length. Now if it is moving perpendicular to this, then this is the direction. If it is moving at some angle theta, okay, let me write that case too. So here I hope you are understanding. I am trying to explain every case, in which case what will be the EMF induced. So in this situation, again let's say this is the space and all that magnetic field is present, and this is my random shape conductor and its joining length is L, but it's now this conductor is moving this way actually. So it's moving this way at some angle theta, is it? So now it's basically, you can write this curved length is equivalent to this length L, and now but this length L is not moving this way. You can write it's moving this way with only V sine theta plus it's moving v cos theta with this velocity in this direction. So this will not cut any flux, or there will not be any change. There is no field lines cut by this velocity, only this will be the resultant velocity. So in this case, if this is AB, and so I can write EMF across AB in this wire also will be BVL sine theta. Remember that. So this is about EMF, motional EMF, induced EMF. I hope you are clear with this part up to here. Let's see some application of this part. We will solve some problem based on it. Okay, so let's see some application of motional EMF. So here we have one problem. A rod is kept parallel to a long wire carrying constant current I. So this is a long, infinite long wire carrying constant current I. A rod is placed length L parallel to this wire, and rod is moving away from the wire with constant velocity v, and it's given constant velocity v away from the wire as shown. Find the EMF induced in the rod when it is at a distance x. So it's asking the EMF induced in the rod at a moment when the rod is at a distance x from the wire. So we can solve it easily, right? We know EMF induced is given by V into L. The point here is that B, due to this wire, is it at distance x, so I can write B is equal to what? You must remember this, mu naught into I divided by 2 pi into x. So the thing is that this x will be changing and B will be also changing. So the EMF induced in this wire will keep on changing with x. But it's asking about the EMF induced at one particular moment of time. So we can calculate that easily without worrying about the change, is it? So one way is, we know already the formula. If magnetic field at some point is B and velocity V, length is L, then by this I can write EMF induced is equal to B is what? Mu naught into I divided by 2 pi x into V into L. So this is the EMF induced. Another way is, we can solve it in terms of, like, let's say for a small interval dt, I can take this, it is moving by just a small distance. So for this is, let's say, V dt, right? Then I can write for this reason, small distance, I can write B is almost constant. So this is one way, and this is your final answer. We got it already. I'm telling you another way also. So another way is, you can calculate in this dt time, this is the distance moved by the rod, area covered by the rod is LV dt. So magnetic flux change, is it, or change in magnetic flux in time dt, that is equal to BL V into dt, and this implies d phi by dt will be again BLV, and you can substitute B, because for this small distance I can take almost B is constant. That assumption I need to take. So that way I can add B is equal to again mu naught I L V divided by 2 pi into x, and we are getting same EMF, right? Here direction of EMF you can even calculate by just, you can check that on a electron in which direction force will be acting, is it? So here you can see the force on electron here, force will be like Q, V cross B. So B will be in inward direction, V cross B. So force on positive charge will be upward, then on electron it will be downward, is it? So here it will be like negative charge, so the polarity will be like this. So it will be positive end, and this will be negative end, right? So this is the magnitude of EMF induced. Let's see another problem here. A rectangular loop as shown in the figure move away from infinitely long wire carrying constant current I. Find the EMF induced in the loop. So it's also a similar problem. Here we can see infinite wire, and this is a loop. So you can just imagine here magnetic field will be again inward, right? And now just imagine this, let me write it A, B, C, D. So as this loop is moving away, I can directly write the EMF induced in AD and CD part will be 0. EMF induced in AD and BC will be 0. See, straightforward, because it's like no electric field, no magnetic field lines are cut by AD and CD part. But yes, in AB and CD there will be EMF, is it? But in AB and CD there will be induced EMF. Clear? So I can write induced EMF, let's say, and again the polarity exactly by same way I can write polarity will be, so if I am writing it, this is, so here polarity will be like this way, and here also polarity will be, so this is A, B, C, D, right? So this is, let's say, right, E1 and this is E2. And E1 I can write, E1 is equal to what? B means mu naught into I divided by 2 pi x. This distance x into L into V. So this is E1, and E2 is equal to what? Mu naught into I divided by 2 pi. Now distance of AB from wire is x plus B into L into V. So we got E2, and here you can see E1 is greater than E2, so the EMF in the loop will be what? This is higher, so as we are moving this is plus and this is minus, so EMF in the wire, EMF in the loop, you can write it's E1 minus E2. You can just simply substitute and we are getting finally it's mu naught into I LV divided by 2 pi. I am taking it out, and this will be like 1 by x minus 1 by x plus b. You can simplify it further or you can leave it up to here also. So this is your result. It's simple thing here. What we did is actually here, like this is one wire like carrying current infinite long, calculated magnetic field B this, and at a time this is the formula we substituted, we got the EMF. Here what is happening, we can just loop can be treated like two wire AB and CD, because in BC and AD there is no EMF induced. So we got EMF induced in AB part and EMF induced in, basically this is in CD part and this is in AB part. This is higher, so we can get the net EMF is difference of that E1 minus E2, and this is your result. You can simplify it one step forward. So this is about application. We can try more problem based on it. So let's see in the next class. Okay, let's see few more cases, few more problem here. So we have one problem. A rod of length L, this is a rod, is placed perpendicular to the long wire carrying constant current I. So this is a long wire carrying constant current I, and a rod of length L is placed perpendicular to this wire as shown. And the rod is moved parallel to the wire, so it's given velocity v with parallel to the wire and with constant velocity v. Find the EMF induced in the rod if its nearest end is at a distance of a from the wire. So this nearest end of this rod, it's A and B, is at a distance a and length of the wire. So this is the situation given to you. Now you are asked to find the EMF induced in this rod. Now see here, what we can do is we can like consider here, let's say after some time the rod has moved here. In this situation, if I am taking the like calculating the flux changed by this rod, then I need to actually integrate it from here to there. So one way is you can consider this length as, let's say, V into dt, then it's like this width is like V dt and its length is L, so area will be L into V dt. But because the magnetic field is not constant at every point, so I need to consider one small element is it? And then I need to find the B at this point and find B into dA area, then flux, and that I need to integrate it for this area. Then I will get total flux and divided by dt, I will get EMF. So that will be like little bit lengthy. We have another way. There also we need integration, but we can go easier little bit comparatively. So the another thing is that I can take a small element of this rod. Let's say this is my here I'm taking from here, it's let x, and this length is dx. Okay, so for this dx length, dx element, I can take almost my B, magnetic field is constant. So let's see here. So let's consider a small element of length dx, right, at distance x, and for this small element I can take almost my B is equal to constant, and B is equal to what? Mu naught into I divided by 2 pi x. So now I got B, I got its length is L and velocity is V. So EMF induced in dx length, so that let's say DE, it can be written as B into V into dx, and that is mu naught into I divided by 2 pi x into dx multiplied by V. So this is the EMF, total EMF. I can now integrate it, and that will be from A to A plus L. So EMF I am getting, this is mu naught into I into V divided by 2 pi, and integration of dx by x will be ln, and substituting the value L plus A divided by A, and this is the EMF induced in the rod. So this is the easier way. Another way I told is that I took small like length VDT covered by this rod in delta t time. So my total area will be this length L into this width L VDT. But the point is here the magnetic field is not constant, so I need to calculate the flux through this area by integration, and that will be little bit lengthy. You can go that way also. I have just solved it. Another way is simply take a small element, because we know if magnetic field is B, length is L, and velocity is V, then EMF induced in that is given by BVL. So I have taken that small element because B is not constant, but for this small element I can take my B almost constant. So for this small element I can write DE is given by this, and then I can integrate, I will getting this. So this is the EMF induced in this rod. Let's see another problem here. A rectangular loop is moving parallel to a long wire carrying current I with the velocity V. So here same situation, almost just like this. Here a long infinite current carrying wire carrying current I. Instead of wire we have here, here we have one loop, and let's say this is a loop A, B, C and D, and this length is B, and this end is at a distance of A from the wire. This length is L, and it's moving this way parallel to the wire with velocity V. So now in this situation you can, I think, easily imagine, because this CD and AB wire are not cutting any field lines, so EMF induced in CD, and here I can write EMF induced in AB and CD will be directly 0. I can write, because no field lines are cut by AB and CD. Only EMF will be in BC and AD, and this BC situation is just like this situation, so I can use this result there. So EMF, let's say in first thing is, what will be the polarity here? I have not mentioned it here also. For that you can just go with the force on a positive charge particle, and that is Q V bar cross B bar. So V bar cross B bar, so that will be like right direction. So force on positive will be this, negative will be this. So you can just imagine this will be positive polarity, this will be negative polarity. So here also you can write this will be positive, this will be negative. So now I can write here EMF in BC, let me write it's E1, that is equal to what? mu naught into I divided by 2 pi into, this is L into R. Just 1 second. Yes, mu naught into I into V divided by 2 pi into ln. This will be like A plus B divided by A. So this is EMF1. Similarly, EMF in AD can be written as, let's say, E2, and that is mu naught into I into V divided by 2 pi and ln. This is A plus B divided by A. So this is EMF E2 and this is EMF E1. Now you can see here, these two EMF are actually equal. So if I go for the loop, EMF induced in the loop, here the polarity will be like this and polarity will be like this. So if I am going in the loop, then net EMF will be 0. So here you can write EMF induced in the loop will be is 0. So in the loop total there will be no EMF. So if resistance is there, there is no current in the EMF, current in the loop. So this is a next problem. So I hope you should be finding them easy, not much difficult. Yes, it's new problem. You should learn the approach, you should learn the process, how we deal, how we solve such type of, because next problem will be similarly like based on these things. So you should extend these concepts, then you will be like able to solve even little bit complex problems. So this is all about these two problems.